Hi everybody, my name is Andrew Novins and this video is the second in the series that talks about how to take our MicroStation models out to the Unity game engine and then from there to the HTC Vive virtual reality headset. This video is intended to be viewed in conjunction with a written tutorial that I've posted on Bentley's MicroStation Visualisation forum. And in this video we will talk about the importance of surface normal direction, how to go about creating a collision mesh for use within Unity, and then how to export our MicroStation files to the FBX file format. So here in Unity, we have a simple scene with some simple geometry, in this case a rectangle that represents this chain link fence. It has this material applied to it. Now the reason that surface normal direction is important within Unity is that the standard shader within Unity only does single-sided rendering, which means that any shape will only have its front face rendered with the texture applied to it. The back face will be invisible. So here, if we rotate to the back of this chain link fence, you can see that the texture is now invisible. And for the most part, this is not what you want. So it becomes important then in MicroStation to make sure that our surface normal directions are always pointing in the correct direction. This is made a little bit more difficult in MicroStation because MicroStation does not render single-sided shapes. It actually renders both sides of a shape. So here I have a floor, and if I rotate the camera angle to look at the bottom of the floor, I can still see it in MicroStation. Whereas in Unity, that floor would be invisible. So from within MicroStation, it becomes a little bit difficult to know whether your shape will be visible in Unity or not. So it really comes down to you as the modeler to be diligent in drawing your shapes properly. Now you can check the surface normal direction by clicking on the change surface normal tool and then clicking on your object, and here you can see that the surface normal direction is pointing up, which is what I would have expected. Now for most textures, it really doesn't matter, as far as MicroStation is concerned, which direction the surface normal points. So, grass, gravel, brickwork, stone, timber, most of those textures, it doesn't matter which way they're facing, they will look roughly the same. It's really only textures, with text in them that become critical. And so, for instance, if I change the surface normal of this floor and I'll make it point down, you can see here that the text has now been mirrored, and that's not what we want in MicroStation or in Unity. So let's just reverse this once more, and now you can see the text is correctly orientated. Now, how to guarantee that our surface normals are always pointing in the direction that we want is we need to draw our geometry in an anti-clockwise direction. So here I've picked the place rotated block tool, and so I'm going to deliberately draw it in an anti-clockwise direction. So I'll place my first point here, my second point there, and my third point up here. And now you can see that the texture has text in it that's readable. If I had, let me undo that, if I had drawn the shape in a clockwise direction, so I'll place my first point there, second point there, and third point up here, now you can see that the text is mirrored, and that's not what we want. So you do need to be careful and make sure to always draw your geometry in an anti-clockwise direction. Now, MicroStation sometimes doesn't quite help us out in terms of making sure that all of our geometry has textures orientated correctly and the surface normals pointing in the correct direction. It's unfortunate, but MicroStation's mirror tool and MicroStation's change surface normal tool both tend to ruin the orientation of textures once the object is mirrored or the surface normal is reversed. So to show you what I mean, here we have our original shape, and I've placed it, and so this is the front view, and I've placed it in an anti-clockwise direction. And so I'm now going to do a mirror copy. So I'll take this and I'll mirror copy it over to here. And so as you can see, the text is now reversed. And what's happened is that the surface normal direction has also been reversed. Now, that's not terribly helpful, and I wish the mirror tool would be improved to do this better. Currently what happens is the mirror tool, so the original shape has its origin down here, and the second point defines the baseline of the texture, and the third point defines the plane orientation. But the first 2 points are the crucial ones. And so they defined that this texture was created in an anti-clockwise direction. What the mirror tool has done, it's mirrored our geometry and it's taken the origin and it's put it over here. The second point of this mirrored object is now here, and the third point is here. And that's why now when we look at our geometry from the reverse side, this mirrored object looks as it should, as though I had drawn it with the intent of having the surface normal facing me this way. And in fact, you can see 1, 2, 3. The orientation of that is anti-clockwise, and in fact, the text is readable, and it's as though we wanted it to be facing this way. But I didn't want it to be facing this way. I actually wanted the object to have the texture facing out this way, just like this original object had. So unfortunately, the mirror tool does this with the point order. What I wish that the mirror tool had done is, yes, mirror the geometry, but then I wish what it would have done is taken the origin and moved it to where point 2 is. And then take the second point, point 2, and reverse the direction and put it where point 1 was. So that now defines the origin and then the direction, which is anti-clockwise, and then by extension, point 3 then has to be here. So this is what I wish the mirror tool had done. And then if it had done that, I would have ended up with a shape that looked like that, and I can read the text. But it didn't do that. So this is what it did. So you might think, okay, well, this is what the mirror tool did, so maybe I can reverse the surface normal. So let's try that. And we reverse the surface normal. And now the surface normal points out as it should. And okay, yes, I can now read the text, but unfortunately the texture has been rotated 90 degrees. And so what's happened is that the change surface normal direction tool has left the origin where it was, and it changed the direction of the points. So it basically took point 2 and put it up to here, and then by extension point 3 has to be there. Now, this is not what I wanted the change surface normal tool to do. What I wish, I just went undo there. What I wish the change surface normal tool would have done is I wish that it would have done what I wish the mirror tool would have done. And that is, I wish that the change surface normal tool, this one, I wish it would have taken the origin, moved it to where point 2 currently is, reversed the direction and put point 2 where point 1 used to be, and then by extension point 3 has to be there, and then you end up with a shape that has this has an anti-clockwise creation order. So both the mirror tool and the change surface normal tool have a tendency to destroy your textures. So my radical advice is that you don't use the mirror tool and you don't use the change surface normal tool unless you have to, or unless it's irrelevant how the textures are orientated. So for grass, gravel, maybe brickwork, but probably not, timber, and so on. So it's something to be careful about. You really need to draw your geometry properly and hopefully not mirror it. It's sad, but it's true. So that's kind of what you need to be on the lookout for with regard to surface normals and then their impact on Unity. So MicroStation does two-sided rendering, which hides some of the problem and makes it worse for Unity. But we won't be using Unity's standard shader. We'll be using the lab renderer, and the lab renderer uses, over here you can see it uses the Valve VR standard shader. So this is the standard Unity shader, and this Valve VR standard is the one that we're actually using. Now this shader has an option to do backface rendering, and so for the chain link fence material, I can turn on backface rendering, and when I do, you'll see here in the preview that you'll see the back of the sphere. So let me just do that. And now you can see the back of the sphere. And then let's come up into this view, and then if we look at the back of the chain link fence, this time we actually see a texture. It's magic. It works really well. So we definitely want to use the lab renderer. We definitely want to use the backface render option on geometry that deserves it, but we don't want to use it on everything. There will be a performance hit if you turn it on for everything. So for instance, brickwork walls. If I had, I mean, here I've drawn this brickwork wall with the surface normal pointing in the correct direction, and that's why I can see it in the camera, and it's not invisible like the back of this was. But if I had made a mistake in MicroStation and had the surface normal pointing in the opposite direction, now here in Unity that would be invisible. And so what you shouldn't do in Unity is go, okay, my brickwork is invisible, let's just make it double render the back face as well. Don't do that. It'll just give you extra overhead when you don't need to. The correct solution really is to come back into MicroStation and change the surface normal if you can, or simply redraw the geometry with the correct anti-clockwise orientation, like this. So, yes, use the backface render option when needed, but don't use it when you don't. Now, that advice really only applies to surfaces. MicroStation obviously does solids, so we can draw solids in MicroStation, and you can see the solids will always have their surface normals pointing outwards, and you'll never have the problem of mirroring, or of having the texture being mirrored. And even mirroring a solid, so even mirroring the solid will ruin the orientation of the texture. So it just goes to show, do not use the mirror tool. Crazy advice, I know, but life will be easier if you don't. So that's the surface normal advice. Now, our MicroStation project is made up of a whole lot of bits and pieces, and all of the stuff that you've drawn in your MicroStation project will be exported to Unity as is. You really don't have to do anything to it except for the surface normal business. But other than that, everything else just goes out as you've modeled it in MicroStation. The only additional bit of geometry that you'll need to draw is a collision mesh. Now, a collision mesh is used by Unity to work out where the player is allowed to go. So in a conventional Unity game, so not a virtual reality game, the player is represented by a capsule which will collide with various elements in your scene and stop the player from falling through the floor or stop the player from moving through a wall. And so we need geometry to tell this capsule where to stop. Now, you do have the option of saying, okay, every bit of geometry in my scene is a collision object and the capsule will bump into everything. Now, there's a lot of unnecessary geometry here that in that case, that the capsule would have to consider as a collision object. And so, for instance, I can show you a project here where I've created some collision meshes. And the idea of creating collision meshes is you want something as simple as possible. So, for instance, these yellow shapes represent my walls. Now, my walls might have all sorts of fancy stuff happening inside them and all sorts of detail and so on. But as far as a collision is concerned, it's all irrelevant. And also, you might have light fixtures which really don't impact how a player should move through a scene. You might have door hardware that's irrelevant for how a person is to collide with the wall. So you really want to create simplified geometry that represents your model. And so, and what's more, so here you can see I have a simple wall, and I've deliberately left out a gap where I've got a door. So in my model, I have a door in this place, but in my collision mesh, I have a gap. So this will allow me as the player to move through the door, even though the door is present in the 3D model. Now this is because I haven't yet worked out how to animate door swings opening when I approach them and so on. So for the moment, I'm just walking right through doors, but I'm not walking through walls. So here's a column and so on. So I've simply created collision meshes. So here I'm outside, and so this is a collision mesh around my cars. It's just as simple as that. I really wouldn't want the entire car geometry to be considered in the collision mesh calculations. I have these represent my people that are in the scene. These red ones represent tree trunks. These cyan ones represent my surrounding buildings. And again, there's no need to have roofs and soffits and gutters and all that sort of stuff considered in the collision mesh. You really want something as simple as possible. In the case of my building here, I've got the roof is represented by this dark blue collision mesh. And so this means that I will be walking on my floor, and then if I shoot my teleporter to land up on the roof, I can land on that blue geometry. So the nice thing about creating a simplified collision mesh is that you can also omit areas of your model that you don't want people to go into. So for instance here, this yellow region here represents a whole bunch of storerooms, which I really don't need people to go into. And you can see I haven't left any openings, any door openings for people to enter that area. So the game object will not be able to enter this region. So that's the other benefit of generating a unique collision mesh. You can control where people can go and where they can't. What more can I say about collision meshes? We'll talk about the settings for collision meshes later on when we create our Unity project. But just be aware that we do need to create a simplified version of our model that represents a collision mesh. Now, I've been talking about collision meshes in Unity for conventional games. In virtual reality, the story is a little bit different because in virtual reality, I am free to walk around my real room that I'm standing in. So if I happen to be standing next to a wall, a virtual wall, but I'm in the middle of my real room, I'm free to walk through that virtual wall and find myself in the space beyond. So in some senses, this collision mesh won't stop me physically from walking through a wall, but it exists to stop the teleporter from teleporting beyond this space. So obviously the floor stops my teleporter from teleporting down to the next level, but the vertical collision mesh objects will stop the teleporter from teleporting beyond them, but it won't stop me physically in my real room from sticking my head through that wall and finding myself in the other space. So even though the collision mesh concept is a little bit different in virtual reality, most of the concepts are the same. You need something for the player to bump into, and that's what this is. So now we'll talk about creating our exported FBX files. So MicroStation geometry will need to be exported into the FBX file format, and then those FBX files will be imported into Unity. Now, what I like to do with my FBX exports is I like to break up my model into smaller manageable components. So in this case, I like to have a FBX export for the ground plane, a separate one for the rocket ship, a separate one for the left gantry, and then another one for the right gantry, and then a fifth one for the collision mesh that you saw here. So the way that I do that is I create a series of reference files. So these are empty files that reference all of my geometry out of this file. So as you can see here, I've created a reference file called collision mesh, and then gantry left, right, ground plane, and rocket ship. And the nice thing about using reference files is, firstly, I can compose my scene, all the elements that make up this particular export file, and I can be certain that I won't accidentally reference in other geometry that doesn't belong, or I can be certain that I won't accidentally remove references that do belong. So this kind of forms a definitive version of what needs to be exported as the rocket ship. But secondly, the reason that it's quite useful to have these reference files is that it's not all projects are drawn at the origin of the design plane. Depending on how you've set up your project, you may be at the design plane, or you could be kilometers. You could be hundreds of kilometers away from the design plane, which actually you don't want to do even in MicroStation. But your project may not be at the design plane, and even if it is at x, y equals 0, it may not be at z equals 0. Often I will set up my projects at x, y equals 0, but I will place them at 600 meters above sea level, because my contours from the surveyor have those levels on them, and it's just convenient to draw it at the correct RL. But for the case of my FBX exports, it really pays to have everything at 0, 0, and I like to have the ground level of my project at 0, 0, 0. So if I just query where my origin is, so you can see here in plan, the origin is here at the center of the rocket ship and here at the base of the rocket ship. So take the opportunity with these reference files to not only use them as a way to cleanly define what's going to be exported in each one of these components, but also move everything to the origin. And so that way, when you get into Unity, you can zero everything at, put all your meshes at 0, 0, 0, and everything will align and work really well. So that's the first thing to note about how to set up your FBX files. And the second thing is to actually do the exports. So we go to File, Export FBX, and so this is the dialog box. And really there are just two things that we have to be aware of. So the first thing is the stroke tolerance. Now for flat square objects, the stroke tolerance is irrelevant, but for curved objects it becomes very important, and this simply defines how coarsely curved objects will be triangulated. So the default units here are meters, so this is implying a 100 millimeter tolerance, and 100 millimeters on this particular model is really quite coarse. It also depends on how close you'll ever come to your geometry. So in this case, I'm going to be standing right next to this rocket nacelle. So it's important that this look round and not polygonal. So in a lot of cases, I might set my stroke tolerance to 0.005, which is a 5 millimeter tolerance. So that's a good start anyway. The other thing that you'll have to set is down here is to invert the Y and Z coordinates. Now MicroStation uses a coordinate system which has X and Y in the horizontal plane, and it has Z in the vertical plane. And we're all used to this, and that's all we've known for many, many years. But Unity doesn't use this particular coordinate system. Unity has X in this direction, but it has Z or Z in this direction. And it has Y in the up direction. And boy, is that hard to get your head around when you've spent your whole life doing X, Y, and then Z in this direction. But nevertheless, you simply have to invert the Y and Z coordinates. So that's all you have to do, and then just export. So this is my rocket ship, and I will export this and overwrite the existing rocket ship FBX file, and then I take those FBX files and drop them into Unity, and Unity reads all the new changes, and that's all that you would need to do. So there's no need for me to export, I've already got them. So as you can see here in my project, so this is my MicroStation project, and I have already exported my collision mesh, the gantries left and right, the ground plane, and the rocket ship. And so the next stage will be for us to copy these files to our Unity project. But that'll be part of a later video, and so that's it for now. And I think the next video will be covering we will be creating our Unity project, and we will add the scripts and prefabs from the imported assets. So that's it for now, and thanks. Bye.